David Kant here with another question bank question in topic 12.2, and we're looking at alpha particles approaching a nucleus. We have an alpha particle approaching a nucleus of palladium. The initial kinetic energy of the alpha particle is 3.8 MeV. It's brought to rest at point P, right here, at distance d from the center of the palladium nucleus. It then goes back out the path from which it came. So what we see is that the alpha particle is fired in with a certain amount of initial kinetic energy, 3.8 MeV, and as it approaches the palladium nucleus, it slows down until it stops, turns around, and accelerates back out. And the reason it does that is because the alpha particle itself is a nucleus. It's a helium nucleus, so it's positively charged, 2 protons, 2 neutrons. And the palladium nucleus is a nucleus, so it's positively charged, and so they repel each other. As the alpha particle approaches, it slows down, stops, turns around, and goes back out. Calculate the value in joules of the electric potential energy of the alpha particle at point P, right here. The question then takes the interesting step of saying, explain your working. So we can't just come up with the answer, we have to tell them what we're doing and why. Now the idea here is that the initial kinetic energy of the alpha particle becomes electric potential energy. We're losing kinetic energy as we gain potential energy, and at this point, all of the kinetic energy is gone. We've reached our maximum potential energy. So we get to say that the electric potential energy at point P is equal to the initial kinetic energy, which is 3.8 MeV. So that is the potential energy that we're looking for, but the question does say that we need the value in joules. So we need to do a conversion. 3.8 MeV is 3.8 times 10 to the 6th eV. And to turn that into joules, we just need to use the conversion 1.6 times 10 to the negative 19th joules per eV. Now if I multiply these two, then eV will cancel, and I'm left with joules. Plugging that into the calculator, I get 6.1 times 10 to the negative 13 joules. Part B says the atomic number of palladium is 46, and it gives us a hint there. It tells us it means there are 46 protons in palladium. And I want to calculate that distance d, the distance of closest approach. This one right here. Well, I know what the potential energy at point P is, and I know how to calculate the electric potential energy for 2-point charges. It's K, Q1, Q2 on R, the separation between them. I'll call it D in this case, since the question uses the symbol D to represent their separation. Solve this for D, and we get that the distance is equal to K, Q1, Q2 on the electric potential energy, which we know from part A. So we know all of these things, we can plug them in now. D is equal to 9 times 10 to the 9th. It's Planck's constant. Excuse me, not Planck's constant, Coulomb's constant. 9 times 10 to the 9th K. Q1 and Q2 are the charges of the two particles. So one of them is the alpha particle. There are 2 protons, each with a charge of 1.6 times 10 to the negative 19th coulombs. And the other one is the palladium. There are 46 protons, each with a charge of 1.6 times 10 to the negative 19th. So 1.6 times 10 to the negative 19th shows up twice in the equation. And we'll divide all of that by the potential energy, 6.1 times 10 to the negative 13 joules. That goes into the calculator, and we get 3.2 times 10 to the negative 14 next up it says gold has an atomic proton number of 79. Explain whether the distance of closest approach of the alpha particle to a gold nucleus would be greater or smaller than your answer in B right here. So gold has more protons than palladium, and if we fire the alpha particle with the same initial kinetic energy into gold, how would the distance of closest approach be different? Well, more protons means that there's going to be a stronger force between the gold nucleus and the alpha particle. The Columbic force KQQ on R squared is going to be greater. So because there is more charge in the gold nucleus, than the palladium nucleus, the force on the alpha particle will be greater, and therefore the alpha particle will have a greater distance of closest approach. Basically, the closest that the alpha particle will get to the gold particle will be further away from the gold particle than the closest it gets to the palladium nucleus.